Hey guys, in this video I will present a solution to problem A1 from IMOC 2023. We are asked to find all functions f from the positive integers to the positive integers with the following property. For every positive integer n, we find exactly one positive integer kn, such that if we apply f kn times on n, the result is less than or equal to n plus kn plus 1. For example, the function f von n equals n plus 1 does not work, because then for any value of kn this would be true, and so kn would not be unique. By this investigation, we see that f von n equals n plus 2 does work, because the value kn is equal to 1 will indeed be a solution. We have f of n equal n plus 2, which is less than or equal to n plus 1 plus 1, and all larger values for kn do not work, so I will note down this first solution. Let's notice that we can use the same inequality with f of n instead of n in a really nice way. Namely, if we call f of n m, then we know that f of km of m is less than or equal to m plus km plus 1. The left side is nothing but f of km plus 1 of n. Because kn is a unique integer with that property, we can read off from this inequality that we must have kn equal to km plus 1 if m is sufficiently small. In particular, if we assume that m is less than or equal to n plus 1, then we will be exactly in that case. Namely, we obtain that f km plus 1 of n is less than or equal to this quantity, which in turn is less than or equal to n plus km plus 1 plus 1. Therefore, we can conclude that kn must be equal to km plus 1. On the other hand, we have f of n equal to m less than or equal to n plus 1. Taking a look at the inequality, this immediately gives us that we also must have kn is equal to 1. And this is of course a contradiction, because km is greater than 0, and so these two values are distinct. In other words, we can conclude that the assumption was wrong, and therefore we know that f of n is greater than or equal to n plus 2. We already found out that f of n is equal to n plus 2 is the exact perfect growth rate to hit this inequality on the first go and not after that. Therefore, we can use this inequality to bring the following assumption to a contradiction. Namely, we assume that m is greater than or equal to n plus 3. Combining this with the fact that we always have f of n greater than or equal to n plus 2, we can conclude by induction that we have fk of n greater than or equal to n plus 2k plus 1. Since we only consider positive k, so we have k greater than 0, this is always strictly greater than n plus k plus 1. Of course, this contradicts the existence of such a kn, and therefore this is also a contradiction. In total, we found out that f of n is greater than or equal to n plus 2. Now also f of n is less than or equal to n plus 2, and therefore this is indeed the only solution, and we are done.